This video is on the objective solve trigonometric equations using fundamental identities. And this is the second video on this objective. Hopefully you saw the first one. And I'm not going to be going over all the different fundamental identities you should know. Remember there were the reciprocal, quotient, Pythagorean, even, odd, cofunction, the the sum and difference formulas, the double angle formulas, the half angle formulas. There were a lot of identities that you've come across up to this point. And in the first video, I only used a certain Pythagorean identity and an even odd identity to help me simplify an equation and solve it. We're going to be doing the same thing here, only possibly using a different set of identities. Alright, so again, you might come across problems where you have to use different identities, right? I'm not going to do every single possible scenario you'll come across. Alright, but I just want to show you that you can use these identities to help you simplify equations into either like a linear equation or a quadratic equation that you should be able to solve based on your experience from previous assignments and previous objectives. Alright. So if you'd like to see some more of what they have to say about this, or you're unfamiliar with the topic, click on More Instruction and look at their videos, their notes, their examples, and hopefully those help. So it has to solve the following equation for alpha. Right, but not find all the solutions for alpha, all possible alphas. They just want the values of alpha that make this true that are between 0 and 2 pi. Right. Now notice here, I'll write it out. Let's go to a piece of paper. I'll write out the equation. So we're given here 3 times the cosine of 2 alpha plus 2 times the cosine of alpha minus 5 equals 0. Right. Now, yes, there's only cosine, but they have different angle measures, so these are different values. Right? The cosine of alpha is more than likely different than the cosine of 2 alpha. Right. So what I would like to do is use an identity that I know to rewrite this so that every trig function has the same angle in it. That would be actually really nice. I'd prefer that. So what I'm going to use here is one of those, this is the cosine of 2 alpha. I'm going to use one of those double angle identities, right? One of the double angle formulas. Now if you recall, remember the cosine of twice an angle, say 2 alpha, there were 3 different versions of this. One was cosine squared alpha minus sine squared alpha, but I'd rather not introduce another function if I don't have to. Right now everything's cosines, so I'd rather not introduce a sine as well. Right. But there was a version that only involved cosine, and I'll write it now. Right, the cosine of 2 alpha was 2 times cosine squared alpha minus 1. There's the version. That's if I took cosine squared minus sine squared and then replace the sine squared with 1 minus quantity 1 minus cosine squared and distributed and combine like terms. Right? Hopefully you remember this. Hopefully this rings a bell. So I'm going to make this substitution into my equation, and then I'll have just nothing but cosine alphas, right? Without, they'll all be the same unknown and not different unknowns like these two are. Okay, so this left side now is 3 times the quantity, right? I'm replacing this cosine of 2 alpha with what I said here using the double angle formula, which is 2 times cosine squared alpha minus 1. We'll distribute that 3 in a second. And then I got plus, plus 2 cosine alpha, and then minus 5 equals 0. And I'm going to distribute this 3, and we'll combine like terms, and you're going to see this is exactly like a quadratic in cosine. I'll have 6 times cosine squared of alpha, right? Then plus 2 cosine to the first of alpha. And then 3 times negative 1 is negative 3. Then you have the minus 5, be negative 8. And then you have equals 0. So you see how this is like a quadratic? This is like 6. You have cosine alpha here, but it's squared. So this is just like this. If I were to make a little substitution, just so I don't have to keep writing the cosine of alpha all the time, I'm going to replace, every cosine of alpha I see, I'm just going to replace it with x. Alright, so this is just like solving 6 times, x squared plus 2 times x minus 8 equals 0. Alright, what I'm going to do is solve this for x, and then we're going to go back, substitute back, and solve for alpha. Alright, now something I'm noticing here is that all these have a factor of 2, so I'm going to divide both sides by 2. And we're going to get now 3x squared plus x minus 4 equals 0. Now you could use the quadratic formula. Right, this is a quadratic in standard form, ax squared plus bx plus c equals 0. You could use the quadratic formula, completing the square. However, this one's pretty easily factorable. This polynomial, this quadratic factors, one of the factors is going to have 3x. The other factor is going to have 1x to make the 3x squared. Alright, and then I would need plus 4 here, minus 1 here. And you can check it out, 3x times x, 3x squared. And you have minus 3x plus 4x when you do the outers and inners. That makes plus 1x. And then the lasts make negative 4. Okay. So then you use the zero product property. Remember, when a product is equal to 0 only when one of the factors is 0. So either 3x plus 4 is equal to 0, or x minus 1 is equal to 0. And then solving these for x, we get either, x equals negative 4/3 or x equals 1. Now, again, I don't want to, this isn't the end. I'm not solving for x. I'm trying to solve for alpha. All right, my original equation had alpha in it. So this is where I'm going to substitute back. All right. Everywhere I see an x, that was x was replacing the cosine of alpha. So now I substitute, I'll just say sub back, and x equals negative 4/3 becomes, the cosine of alpha equals negative 4/3, or, another area where I can get solutions here, the cosine of alpha equals 1. And I'll address each of these equations separately. All right, so the first of these doesn't really tell us anything. I'm trying to solve, cosine of alpha equals negative 4/3. Are there any angles with a cosine of -4/3? No. Remember the range of cosine. Hopefully you recall this. Right? The range of cosine was, values from -1 to 1 only. This -4/3 is not in the range of the cosine. This is less than -1. So this equation, I'm going to say, hey, this doesn't give me any information. There are no solutions coming from that equation. So now look at the other one. Where is the cosine of alpha equal to 1? Well, if you think around the unit circle, just one time, the cosine of alpha is 1 at 0. Right? When alpha equals 0, and then plus any multiple of 2 pi, right? Plus 2 pi k, where k is some integer. All right, so I am getting solutions to the equation from this second one. And from this, we see that alpha could be 0, and just keep adding or subtracting 2 pi. Alpha could be 2 pi, 4 pi, and so on. Could be -2 pi, -4 pi, and so on. But they only wanted solutions in this range, right? They only wanted solutions. They only wanted values of alpha from 0 to 2 pi, but not including 2 pi. So the only one of these that is any good for what they're asking for is 0. Right? This is the only value in that range, because 2 pi, that's not included here. So the only solution to this equation that we started with is alpha equals 0. Again, there are others. There are infinitely many solutions to the equation, but the only one in the range they asked for is 0. And you could test it out. Plug in 0 for alpha. You get cosine of 2 times 0, which is the cosine of 0, which is 1. So you have 3 here. Cosine of 0 is 1. 3 plus 2 is 5, minus 5 is 0. That works. Alpha equals 0 works back in the original equation. And that's the only one. So alpha equals 0, the only one that works out. And that is in that range, right? I know you might say, hey, well, what about this one? It says 0 and 2 pi. I already told you, 2 pi is not included in what they asked us for. So 2 pi works, but it's not in this range. Right. So let's be careful with that. All right, so there, I've shown you now a couple examples of uses of identities to simplify an equation. I used a Pythagorean and an even-odd identity in the first video. I used a double angle identity, a double angle formula in this second video. And this is all I'm doing. Again, you're going to be coming across problems where you might have to use different identities, a sum and difference formula, a quotient identity, reciprocal identity, whatever. Lots of them. All right, so I'm not going to keep making videos because I can't possibly go over every possible little scenario you're going to come across. I'm just hoping that you can see from these first two that, it should be possible to use some identities to simplify an equation to one of my liking, and then solve that. All right. So hopefully watching me do this, and looking at the more instruction, reading the answer explanations when you come across them, hopefully all this stuff helps you out when you're working on this material on your own. And thank you for watching.